So yeah, let's start with problem 1. Let me show you first the problem. Yeah. So yeah, as you can see, we have a mixture of dry gas, and that the temperature of the reservoir is the pressure of the reservoir is.
Sorry, are you? I don't know if it's on my end only, but I can only see what you're sharing in a little screen, like the video screen. Does anybody else have the same issue? In the big window, I just see another screen. Use HDMI resolution, blah, blah, blah.
Yeah, we have the
Yes,
same.
on your end.
You have the same online?
Yeah,
No, I can see here.
It's problems I'm showing right now.
Yes, but the way that the ones are connected to the meeting see it is not, I mean, your screen is not projecting properly. We're looking at a different screen you have with a message about the screen resolution. We don't see the problem.
I'm seeing his screen. His actual screen. He's showing
Yes,
us.
it's okay.
Yeah,
He's
okay.
okay? Okay. Okay. There might be something on my end.
See
Okay.
the components and the mole fraction right here, and the reservoir temperature is 140 Fahrenheit, and the reservoir pressure is 3,500 psi. So what do we have to find is formation volume factor of the gas as at 5 points. Yeah, we have the molecular weight of the C7 plus and a specific gravity of C7 plus here. So we go to the camera right now. If I found it, yeah, here. It's my first time using camera, so. Yeah.
Just like this, if you want to see the screen which they are seeing is like this.
Yeah,
Okay.
the camera. Can you push the camera a bit more forward? Yeah. Yeah.
That's okay. Okay. So first, let me sketch the figure of the PVT diagram of the dry gas. As you can see, the phase envelope is like this. So dry gas reservoir. So the reservoir is some kind of like this. So yeah, in the dry gas, as you know, the reservoir temperature is higher than the critical temperature here. As you can see, the reservoir temperature is higher than critical temperature. So we need to find the formation volume factor of the gas, is the ratio of volume of the gas at the reservoir condition over volume of the gas at standard condition. If you use the ideal gas law, you will find this expression. Pressure at the reservoir at the standard condition multiplied by compressibility factor and multiplied by constant R and multiplied by reservoir temperature over temperature of at the standard condition and multiplied by pressure at the reservoir condition. So we have all this info except of the compressibility factor. As you know, the pressure at the standard condition is 40.65. So we don't know compressibility factor, and the R is 10.73. And
no, just move the.
okay.
So maybe you can move it.
Here.
Yes.
Okay. And the reservoir temperature, as we know, I showed you here in the question, 140 Fahrenheit. So converted to Rankine degree is like plus this gives us 600 Rankine. I write it here. So the temperature as at the standard condition is 60 Fahrenheit. Then again convert it to Rankine. And the pressure, reservoir pressure here 3,500. Yeah, but as I told you before, we have to find the formation volume factor at the five pressure points. So we don't use we just write P here, so we can later find for 5 pressure points. So here. It's kind of 60 Z over what?
Like, why do we have 1 R here? I mean, it should be 2, and we can like delete them since they're constant. No?
You mean R?
Yeah.
We just have 1 R in the equation.
Yeah, like for the V upwards and the V downwards, each one of them has R up to the equation of PVT, like PV and RT, right?
You are some kind of right. Maybe, yeah, I'm mistaken. Maybe, yeah, maybe I'm just mistaken. So yeah, yeah, we delete both of R. Yeah, okay. We have R right here. So what it remains is 60.48 multiplied by Z and over P. So what we have to find right now is to find compressibility factor for in the 5 pressure points. we make a table here. So what do we have here is component C1, C2, C3, so C4, normal C4, and C7 plus. Yeah, also the mole fraction in the question.
Sir,
Yeah,
why did you cancel the R?
because we are dividing the V over V in that equation.
Yeah, I know, but I think there is no R in the standard condition here because also I've checked the compendium.
Okay.
Yeah, the R is in the VG reservoir section. So in the numerator there is R. However, in the denominator there is no R.
Oh yeah.
He said
Yeah, you can check the compendium also. So
There is
you know,
no.
sure. The compendium reservoir fluids, each 18, 8 to 18, and also the equation is 8.18. I can share my screen if you want to to show you.
Yeah, you can.
Okay, but you have to stop sharing. Can you see it, sir?
Yeah, I can see it.
Yeah, here there is the R. However, in the denominator there is no R. So this might be a question why there is in the numerator and why there isn't in the denominator. But this is the real question, the real equation that we have to use, I think.
Yeah. So we just follow this equation. Yeah.
Okay. All right. Okay. Now I'll stop sharing.
Generally, we don't have to have R inside. You were right.
Yeah.
And in the compendium, it is wrong to have the R because generally I check the BG.
yeah, although on internet they don't show R at all.
Maybe
The R.
If you write the PV is equals to NRT,
yeah.
you will
Exactly.
get the R's disappearing.
Yeah, maybe there is a.
I personally asked him when he was in the class. I told him the R is extra, and he told me, okay, R has to be omitted. We have to modify it.
Yeah,
Okay.
he said that.
So we don't have any R inside the
Yeah.
equation.
Also here, like I have the equation of dry gas. There's like both R's, and you just delete
Exactly.
all of them.
Maybe there is a mistake in the compendium. So
Yes.
I will ask him, and next time I will give you answer. Yeah.
So we do without R for today.
Yeah, without R today, and next time I will ask him. So we need to find the critical temperature and the critical pressure, and here mole fraction multiplied by critical temperature, and here multiplied by critical pressure.
So you use this to find your pseudo-critical
Yeah,
pressure.
we are using this to pseudo-critical. Yeah. Yeah, you can find this data in the compendium. Do you want to show you or something? Compendium? Yeah.
What exactly one is
The critical temperature and critical
why is
pressure.
that percent of the gas and mixture?
Sorry?
Why is like the percent of the mix of the gas?
Yeah. Mole percent. Yeah, right.
Okay, so this table 8.1. Yeah.
So here, yeah. You can find the critical temperature here and critical pressure here over here. Yeah. Also molecular weight here. Maybe we need that in next questions or something. Yeah. Also there is information for N2O2, CO2. Yeah. Get back to here. Just write down the information we got.
Where did you take your values from?
Sorry?
The values.
From the table that I showed you.
Does the table have a different unit? I think so, right?
Oh, there was.
That's slightly different.
They're different. That's no problem. You can correct it next time.
The one which you have is in Kelvin. One you have over there, I think it's
Ranking.
Fahrenheit or ranking. Yes,
It's ranking.
here is Kelvin.
No, it's ranking in the compendium. It's ranking table.
It's compendium.
In the Excel.
You just have a slight difference between them.
Excel sheet.
Yeah. It's different everywhere.
It's in ranking, so yeah, this is in PSIA. So you can find the C7 plus in the table that I showed you. So we have to find it. I will leave it then show you.
Sorry, do you get the C7 plus?
Yeah, I will show you after.
Okay. So at the end, are you using a different table? It's not the one in the compendium. You're using one that has slightly different values. Is that what you said?
Maybe I use the different table, but it is better for you to use this table in the compendium.
Okay.
There is no high difference in numbers. Also, critical pressure of C7 plus, we'll find it later. So multiplying mole fraction by the critical temperature that we have here, multiplying by that, give us so we do it for all of the data. And multiplying mole fraction to the critical pressure, can write so to find critical pressure of C7 plus, we can use the something like that figure. I couldn't find that in the compendium, but maybe I will upload it later in the canvas. In this text is a critical pressure, and here molecular weight of C7 plus, something like that figure. Each of these are the specific gravity of C7 plus. For example, it's weight 8, maybe 6, maybe something like that. So we have the molecular weight of C7 plus. Also, we have the specific gravity of C7 plus. So easily we can find something like that, critical pressure of C7 plus. Also for critical temperature, C7 plus, something here is critical temperature. Here is also molecular weight of C7 plus. This is like that. Gravity.
Can you please upload those curves when you have some time after this? Because
Yeah, sure.
thanks.
So we have the both of this data. Easily find critical temperature. Back to the table. Find critical temperature is 0.9, and the critical pressure is so multiplying by mole fraction. Also, so now we have to find the pseudo-critical pressure. That is sum of all critical pressures in the table multiplied by mole fractions, and also for pseudo-critical temperature, sum of all critical temperatures multiplied by mole fraction. You can see sum of all of these. So we write it here. Sum of this one. Write it here. This is in ranking. This one is PSI.
Sorry, one question about the C plus again. So
Yeah.
that the information we were given about the molecular weight and density is what you use in those curves you're gonna upload.
Yeah, we have given the specific gravity and the molecular weight. So
And with those, you go to the graph and
yeah,
find the temperature and pressure.
Yeah.
Okay, thanks.
So first, we find the formation of volume factor at the pressure of 100 psi. This is compressibility factor. So right now we find pseudo-critical pressure and pseudo-critical temperature. Now we have to find the pseudo-reduced pressure and a pseudo-reduced temperature. So pseudo-reduced pressure is equation of pressure over pseudo-critical pressure, and so the reduced temperature is temperature over pseudo-critical temperature. And pseudo-reduced pressure at 100 psi. We also found the pseudo-critical pressure that was 659.4, which is was the 0.15. Also pseudo-reduced temperature. Need to find at the temperature of that is 600 ranking. So here over so now we have the pseudo-reduced properties. Going to the standing cuts figure and find the compressibility factor. So let me show you the standing cuts figure. Yeah. I think we don't have another one. Oh, that's yeah. This is the standing cuts figure. So in the x-axis, we have a pseudo-reduced pressure here. And in the figure, you can see the line of these lines are pseudo-reduced temperature. By having those data, you can find the compressibility factors for each pseudo-reduced properties. Compressibility as at 100 psi is equal to 0.985.
Sir?
Yeah.
So the BG constant that you have found, 16.48,
Yeah.
this value should not include the R, right?
There's just one R in the
Yeah.
Question, yeah.
I was now checking it, and it seems out that in the compendium it's wrong. I have found it in PetroWiki, which is sponsored by the Society of Petroleum Engineers.
Yeah.
There is no R, and if you want, I can again show you. In the compendium, it is wrong. There should be no R. R's will cancel each other. So what I think is that this BG equals 16.48. This does not account for R. So this constant has not been multiplied, like the numbers have not multiplied by R.
Yeah, okay. So yeah, we cancel out the R's here, yeah?
Yeah, these R's will cancel each other. However, in the compendium, it's wrong, and I think that the lecturer Professor Strand should be informed about this.
Yeah, to be sure, I will ask him later, yeah. But now you just cancel it out to R's, yeah.
And the value that you've got, 16.48, is like it does not include the R.
Yeah, okay, so yeah.
Okay.
So
can I ask something? Can you hear me?
yeah, go on.
Okay. Yeah, we got a pseudo reduced pressure at 0.15.
Yeah.
And the standing cuts scale starts at 7, was it? So how did you get the set factor?
Yeah, there's a top section of the figure that starts with the 0, I think, yeah?
Yes.
Yeah.
Oh, okay.
So we found the compressibility factor for 100 psi. Then we can go on for other pressure points easily.
I also have a question. So we have found that compressibility factor for the specific pseudo-reduced pressure and temperature.
Yeah.
But looking at the spreadsheet of the solutions of the exercises, they also calculated a compressibility factor for each component of the gas.
Mm-hmm.
And then they calculate BG for each one, I think.
Yeah, each one pressure, yeah.
With a different formula, I think. Are you gonna cover that part?
No, because they use the other equations, and I don't think equations are necessary. Yeah.
Okay, because I didn't understand where they took the compressibility factor. Then they have a hard-coded column in there for each component, but I was not too sure where they took it from.
Yeah, there's a formula. If you want to do it without a figure, yeah. But we just use the figure, yeah, here. It's a standard procedure, yeah.
Yeah. Can you show again, sorry to be a pain with this, can you show again quickly the initial formula that you used for BG, your first paper sheet?
Yeah.
Yeah, that one. Okay.
No.
I just wanted to. Okay. All right.
Yeah. So, as a question, gave us the 5 pressure points here. Make a table to make it easily. for each pressure, we have to find the pseudo-reduced temperature, and also pseudo-reduced pressure, and then by having this, find compressibility factor, and then set over P. That gives us the BG. Z over P, because we have to just find this Z over P here. So quickly just write it here. Because the temperature is constant, they are the same, so the reduced temperature is it's constant for each pseudo reduced pressure. We already find at 100 psi here. Complete the table. Then by having these two, find the compressibility factor with the standing cuts chart. We have the pressure here and the compressibility factor, this ratio with multiplying these data by 16.48. At each pressure. Yeah, that's it. Should we have a break or something? Yeah?
Yeah.
Yeah, okay. So we have a break for 15 is okay? Yeah. So yeah, we have a 15 minutes break and then continue. And ask questions. Let's start with problem number 3. Yeah. So again, dry gas composition with the sampling pressure of 600 psi-J. So we should convert it to psi-A, and the temperature of 92 Fahrenheit. We have also again have a molecular weight of C7 plus and a specific gravity of C7 plus here, and the mole fraction of all the components again. What we have to do is in part A, we have to find the molecular weight of the whole mixture, and then by having that, easily find the specific gravity of the gas, and then we'll find the pseudo-critical temperature and the pseudo-critical pressure of the gas. So let me the pressure is 600 psi-G, and the temperature is 92 Fahrenheit. Converted to ranking gives us 552 ranking, and convert the psi-J to psi-A plus 40.7 gives us 600. So first we need to find the molecular weight of the gas, and then the specific gravity of the gas. For molecular weight of the gas, we have use this equation, sum of all molecular weight of each component multiplied again by mole fraction. So again, we need to calculate all the components molecular weight in the table. Should I draw a table again, or upload it later or something?
I think it's fine.
Write it? No?
No.
Okay. It's something like that. So I shouldn't write this here. can see I wrote all of the molecular weight of each component till the end, and then multiplied each component by the mole fraction of all of them. Then I wrote here the sum of all this column. Just write it here. Sum of all the components gives us 19.49. This is molecular weight of the gas. So for specific gravity of the gas, we have this equation: molecular weight of the gas over molecular weight of air, that is 29 approximately, and from above we have 90.49, gives us 0.67. Now we should find the pseudocritical pressure and the pseudocritical temperature, as the question wants. If we have the specific gravity, we can find the pseudocritical pressure by having this equation. This is specific gravity. So this is specific gravity of the gas in power of 2. And then for pseudocritical temperature, we have this equation.
Where do those equations come from?
There wasn't in the compendium, but in this question we have to find the pseudocritical pressure and temperature in 2 ways. One of the ways is by having the specific gravity of the gas, and the other way is using the table that I showed you. I will calculate it later by having using the table. Okay.
Okay.
But
for those things that you didn't find in the compendium, could you just be sure that you upload them so we can have them?
yeah, sure. Yeah.
In the case of exams, and these formulas are not given in the appendix, and you have got the standing and cards chart, you can use it to.
If some question will, if you all of the information will given in the exam as appendix in the exam. Yeah. So don't worry.
Okay, but if this is not given, that means you request us to use the standing and cards chart to find.
If they give you the standing cards chart in the exam, so use that one.
Yeah.
If the formula, yeah, use the formula.
But as long as we only use those equations if we don't have the chemical analysis.
Yeah, if we don't have the composition of the gas, we use this equation. But as the question says, it says by first find the specific gravity of the gas and then find the pseudocritical pressure and temperature by having the specific gravity. So you have to use this equation.
Okay, thank you.
And another question, for the C7 plus, you mentioned that you will give us the curve that allows you to have to get the temperature, the critical temperature and pressure. But what about the molecular?
You can find it in the question.
Yeah.
It was given in the question.
Oh yeah, sorry. Yeah, that's right.
Also a specific gravity of the C7.
Sure. Yeah.
So let's calculate it. We have time. Calculate it. We find it above. So let's write it quickly. These are the values. And also we have to make some correction because we have CO2 and N2 in our composition. You can see here and here. So we have to make correction. The correction is per mole. So this correction is for 1 mole. So we have to multiply that but by each mole fraction to correct the pseudo-critical temperature and pseudo-critical pressure. For CO2 is 4.4. So we have to add that to the pseudo-critical pressure that we found. And for N2 is minus 1.7. We have to, yeah. So the critical pressure that is corrected is 67.60 that we calculated plus minus 0.7 multiplied by 26. This is mole fraction. This is the correction value. And this is for N2. This correction is for N2. Yes. And this correction is for CO2. So the final result is 670 8.1.
I have a question in there. You're multiplying by the percentage instead of the fraction. Is that correct?
I just multiplied by the fraction, mole fraction here.
But the fraction of the CO2 is not 1.92. I mean, that's the percentage, but the fraction is 0.0192. That will be the fraction, because in the table that is given in the problem, we have a table that is percentage, but that's still a percentage, so it's not still divided by 100.
Yeah,
So
that percentage, so I convert it to the fraction to the percentage and then use it here. Yeah? So this
we
is
shouldn't be multiplying by the fraction, not percentage, right?
because the question gave us these corrections are for per percent of mole, so you have to convert it to mole percent.
Right. But what I mean is those values 0.26, 1.92 were given as a percentage, not as a fraction. Then in your table, the one that you had in your notebook, you had a fraction, which is those values divided by 100, right? Because those were percentages. I thought the formula will be the corrections multiplied by the fractions and not the straight percentages. But if you say that it's the percentage, then
Yeah, this is
then
convert the
so it's
table
always the
to the percentage. Yeah.
okay. So it's always a percentage. Okay, just wanted to be sure.
Whatever the question wants. So don't be sure. So yeah.
Okay, so it's percentage in there. Okay.
Sorry, I also have a question. What the point of this correction? So what does it mean?
It means that if we have N2 in our mixture or CO2 in mixture, we have some errors in calculation. So we have to correct it to give us the accurate values.
Okay, and how do we define such errors?
How do you mean by saying that?
So how do we calculate? Where do we get these errors from? So we do some lab researches or?
Yeah.
They were given in the
Yeah, I
exercise
know,
you
but
have
it's a given. But like in real life, how can we define them?
Maybe you have to ask a schooler to
Okay.
how to find them.
Mm-hmm.
I'm sure for pseudo-critical temperature that is corrected. Use that is here, calculated here, plus the corrections.
And also, I assume we don't have such formulas in compendium, right? Formulas of correction.
Yeah, it is just in the question. It's not the formula, it's just correction. You just have to multiply or, yeah.
Mm-hmm. Okay.
It's just a simple correction. It was for N2 and then and this is for CO2. This gives us
I think it should be minus 1.7, not minus 2.5.
No, it is the temperature, not the pressure. Huh? It's in ranking. So yeah, this is it. The corrected pseudocritical temperature and pressure. We found it. And let's go to the question again. So now we are in part B. Here it says that calculate the pseudocritical pressure and temperature for the C7 plus. I already showed you how to find that by having the figure. Yeah, I showed you in the problem 1. So I don't want to show it again here. And then it says that calculate the pseudocritical values for the gas by using the corresponding state theorem directly. It means that using the pseudo-reduced temperature and pseudo-reduced pressure. Or sorry, the sum of all of the table data to find the pseudo-critical values, not the equation that I gave you in part A.
And you need to use the standard and CADS chart.
Yeah, using the standard CADS chart. This question is somehow silly, I know, but yeah, you have to solve it. Yeah. So, yeah.
Question. In the correction, why did we only use N2 and CO2, not H2S?
Because we don't have this in our mixture composition. Yeah. So let's go to the part C. To find the compressibility factor again and the density of the gas here. So again, let me show you the table here. So sum of this column give us a pseudo-critical pressure, and sum of this column give us pseudo-critical temperature. We need those data to find the compressibility factors. So let's get straight to the values. Sum of all the critical pressure multiplied by mole fraction gives us 678.82 SIA, that is pseudo-critical pressure. And sum of all the critical temperature multiplied by the mole fraction gives us 382.59 ranking. That is pseudo-critical temperature. Now we have to find the pseudo-reduced and the pseudo-reduced pressure and pseudo-reduced temperature. As you know, this question, this equation. Yeah. Pseudo-reduced temperature over pseudo-critical pseudo-critical pressure. Pressure that is given in the question is it was 600, yeah, 600.7 in psi-A, and the pseudo-critical pressure that calculated is 0.80 psi. Is equal to 0.91, and here the temperature that is given is 92 Fahrenheit, that we have to convert it to ranking over pseudo-critical temperature. Often in our ranking, equal to 1.44. So that we have pseudo-reduced pressure and pseudo-reduced temperature. You find compressibility factor, again, standing charts. Z is 0.87 here. Now we need to find the density of the gas. You have to use the ideal gas equation. Is pressure multiplied by volume, compressibility factor. As you know, N, that is number of moles, can be found using M, mass over the molecular weight. here. This is the final question, equation to find the density of the gas. To find the density, we have the pressure. It is given the question, 640.7 multiplied by molecular weight of the gas that we already found in the question, and that was 90.49. We also found the compressibility factor here, 0.87, then multiplied by constant R, and then the temperature, that is 92 Fahrenheit, that we have to convert it to ranking. Final value is 2.325. This is in pound per cubic foot. So the question we have to find it in I think in the gram per cubic meter. So the conversion factor is so this will be in the gram per cubic meter. So at the last part, you need to determine the viscosity of the gas at the 3 pressure points and the constant temperature of 92 degree. And this is in find the viscosity of the gas. At the 3000 psi pressure and the 92 Fahrenheit temperature. So let me show the figure that we have to use to find the viscosity of the gas. You can find this figure in the compendium, yeah. 8. What's happened? Oh.
Yeah, I just provided them. Do you need me to give it to you?
Yeah.
Sure.
Just share it. Yeah.
Okay. Let me join the room. I'm not in the.
Just waiting to open up the compendium 8. So yeah, please wait. It doesn't.
Can anybody see my screen over there? No, that's not this one. I need to show you. Excel sheet. Let me 1 minute to stop the sharing. Courses.
Are you done?
Yes.
Yeah.
I can share.
No.
You found it?
Yeah, I found. So yeah, this is the compendium 8. Go to the end.
That's it.
Yeah. So.
And of course the other one.
So this is the viscosity of the gas at the surface, 1 atmosphere pressure, and the other figure is that you need is this one, the ratio of the viscosity. It is the viscosity of the gas or the viscosity of the gas at the 1 atmosphere pressure. So use these 2 figures to find the viscosity of the gas. Figure of 8.17 and 8.18. In those figures, in the figure that gives us the ratio of the viscosity over the viscosity at the 1 atmosphere, you need to find the pseudo-reduced pressure and the pseudo-reduced temperature in that figure. Then you can calculate the ratio. So again, you need to find that. Yeah. So the critical pressure, and this one, temperature or pseudo-critical temperature. No. The pressure is 300 psia, and the pseudo-critical pressure that we found previously is 678.92. Most of them is psia. And the temperature again is 92 Fahrenheit converted to ranking.
I was 92 degrees Celsius. And the person thinks degrees Celsius.
So this just yeah, just consider the Fahrenheit. Yeah, ignore the Celsius. I think that's a mistake. And the pseudo-critical temperature is 382.5. Right. Ranking, we have found it previously. Then easily found the compressibility factor, 0.74. Use all of this data to find this ratio in the figure. I can again show you the figure. Yeah, this one. We found the pseudo-reduced temperature here, and we found the pseudo-reduced pressure. So easily you can find this ratio. You have this ratio, you need to find the viscosity at the 1 atmosphere pressure. So then we can finally find this one. Again, we have the figure for 1 atmospheric viscosity. And the data we need in that figure is molecular weight of the gas and the temperature of the gas. Let me show you again. Now you have to find the viscosity of the 1 atmospheric. Yeah, you need the molecular weight of the gas here and the temperature of the gas here. Then you will find the viscosity of the gas at the atmospheric pressure. So using that figure, found the viscosity at 1 atmospheric. That is 0.01707. So now we have this ratio. We have also this one. Can find viscosity of the gas. Viscosity of the gas is I didn't write this ratio yet, so just let me. It was 2.2. So multiplying these two values. By this one and this one. This is the viscosity of the gas. Centipoise. So I love. So this viscosity is just for 3000 psi, and because we don't have enough time, so I will leave it to you to find the viscosity at other pressure points.
Can I ask you something? Can you just repeat how did you use the first chart? You have the molecular weight in the x-axis, and I think that's independently on the pressure. That will be the 19.49 that we calculated at the beginning, isn't it?
Yeah, let me share it. You mean this one?
Yes, that one. So we locate in the x-axis the molecular weight, which is the 19.49 that we calculated at the beginning of the problem, I think.
Yeah.
And then what temperature do you use?
Use if the temperature is 92 Fahrenheit. Yeah. You can assume that is 100 Fahrenheit.
Yeah.
You can go from 20 molecular weight to
Okay, yeah, I see that, but I see that in the solution, in the spreadsheet of the solution, they have a different value for each pressure point.
Yeah, maybe they use another equation, something else, not the figures.
Oh no, it's not. No, sorry, no. They have written it 3 times with the same value. No, it's the same value at the end. Sorry, it's just confusing that they copied it 3 times. It's all right.
Yeah. So, nobody have any questions? Yeah, okay. So we finished this session. Thank you all.
So next week Thursday we have 2 hours with you again.
Next week, I think there is one session and that belongs to a school. Yeah.
So let's see.
Maybe.